Hello everyone, my name is Abhijeet Anand and I will be presenting my work on the assessment of sugarcane residues derived biochar for carbon sequestration in the soil in India. It's pleasure to be here at Applied Energy Symposium and presenting this work. India is the second largest sugarcane producer in the world and the largest sugar consumer. The sugar industry is an important contributor to the livelihood of around 50 million sugarcane farmers and half million sugar mill workers in India. It also generates employment through various ancillary activities such as transportation, trade, and supply of agricultural inputs and products. Approximately 34 million ton sugar and 120 million ton sugarcane residues are produced every year by 506 operational sugar mills in the country. About 50% sugarcane residues are utilized for various purposes such as fuel in bagasse cogeneration plants and small-scale rural industries. However, about 60 million tons sugar cane residues remain unutilized. It is very challenging to manage such a large amount of sugarcane residues in the absence of safe and environment-friendly residue disposal system. Open burning is a common practice to dispose of the sugarcane residues, which is a threat to the environment and public health. Biochar conversion of sugarcane residues can reduce GHG emissions by providing a sustainable alternative to fossil fuels and mitigate climate change by carbon sequestration. Biochar is a stable form of carbon which remains unaffected from rapid microbial degradation. Therefore, biochar can provide a climate resilient carbon storage solution. Kuzikov and al. Reported that biochar produced at 400 degrees Celsius could remain sequestrated up to 2000 years in the soil. Furthermore, combustible volatile matters obtained during the biochar conversion of biomass can be utilized to generate heat and electricity. Gaunt and Lehman reported that energy production from combustible volatile matters and biochar application for carbon sequestration could reduce GHG emissions 2 to 5 times more than solely used for fossil energy offset. In the Indian context, with 7.6 gigawatt installed cogeneration facilities, the sugar industry in India is well positioned to provide energy and biochar for carbon sequestration from sugarcane residues. However, there is a lack of information about the biochar usage in agriculture system in India. There are only a few reports on the production, characterization, and use of sugarcane residue-derived biochar for soil amendment and carbon sequestration. This study aimed to quantify the benefits of biochar conversion of sugarcane residues and its application for carbon sequestration in soil. Annual surplus sugarcane residue availability has been considered as the functional unit of the study. In India, sugarcane is crushed and processed at designated sugar mills to produce sugarcane juice. This means that sugarcane residues are produced at sugar mills. Therefore, sugarcane cultivation has been ignored and only residue management has been considered in the study. Sugar mills are located within 25 km reach from sugarcane fields. Sugarcane is mainly carried through diesel-run tractors in India. Therefore, diesel-powered tractors with 1.8 ton lift capacity and farm machineries were considered for biochar transportation and spreading in the field. The energy value of combustible volatile matters released during the biochar conversion has been considered for electricity production and offset the electricity requirement for the biochar conversion and material handling. It was considered that the collection, handling and biochar conversion processes were powered by electricity produced from coal. The sugarcane cultivation system and the system boundary of the study has been shown in the figure 1. Based on the parameters considered in the system boundary, the list of factors used in the study has been provided in table 1. Estimating environmental impacts of biochar application for carbon sequestration at a large scale is a complex phenomenon. The authors attempted to quantify the environmental benefits of sugarcane residues derived biochar application in soil, including carbon sequestration potential, improvement in soil organic carbon and crop yield, and reduction in fertilizer usage, nitrous oxide emissions. Carbon footprint of biochar conversion of sugarcane residues and its handling, transportation, and spreading in the field has also been considered in the present study. Biochar conversion of sugarcane residues, that is sugarcane bagasse and sugarcane top and leaf, was carried out in a batch reactor at 400 degrees Celsius temperature with 10 degrees Celsius per minute heating rate and 1 hour solid residence time in sans oxygen condition. Pyrolysis temperature was selected after thermogravimetric analysis of sugarcane bagasse and sugarcane top and leaf in an inert atmosphere using TGA-DSC3 metal thermal analyzer. Heating rate and solid residence time were selected from the literature. The reactor setup has been shown in figure 2 and TG and DTG profile of sugarcane top and leaf and sugarcane bagasse has been shown in figure 3. Fixed carbon content in sugarcane residues and derived biochar were obtained from proximate analysis using standard methods. Carbon content and the calorific value of sugarcane residues and derived biochar were obtained through ultimate analysis in CHN, elemental analyzer and bomb calorimeter respectively. Experiments has been carried out in triplicates and average values has been considered for all the estimates. Sugarcane residues, pyrolysis and characterization results have been summarized in table 2. State-wise sugarcane cultivation statistics were adopted from Agriculture Statistics at a Glance 2020 published by the Ministry of Agriculture and Farmers Welfare, Government of India. Due to the impact of climatic factors on agriculture production in India, the triennial average of 2017-18 to 2019-20 has been considered as the baseline for sugarcane cultivation statistics to minimize the yearly variation in sugarcane residue generation. It was estimated that India annually produces about 135 million ton gross and 55 million ton surplus sugarcane residues. It was observed that sugarcane top and leaf have about 29% share in gross and 34% share in surplus available sugarcane residues. Administrative boundaries of states and union territories in India has been shown in figure 4. Sugarcane cultivation varies widely in different states due to various factors such as soil type, geographical area, climatic conditions, and irrigation facilities. Statistical data reveal that sugarcane is not cultivated in the states of Goa and Sikkim and Union territories of Jammu and Kashmir, Ladakh, Chandigarh, Delhi, and Lakshadweep. It was estimated that Uttar Pradesh produces the largest quantity of gross sugarcane residue, followed by Maharashtra and Karnataka. Bihar, Tamil Nadu, Gujarat, Haryana, Andhra Pradesh, and Punjab are the other states producing significant sugarcane residues. Uttar Pradesh, Maharashtra, and Karnataka possesses 42 million ton sugarcane residue availability, which is about 75% of total sugarcane residue availability in India. Bihar, Tamil Nadu, Gujarat, Haryana, Andhra Pradesh, and Punjab contribute about 19% to the total surplus sugarcane residue availability in India. State-wise gross and surplus residue availability of sugarcane top and leaf and sugarcane bagasse has been mapped in the figure 5. Surplus sugarcane residue availability has an estimated 18 million ton biochar potential. Sugarcane top and leaf biochar has about 36% share in biochar potential from surplus available sugarcane residues in India. It was observed that state-wise biochar potential followed a similar distribution pattern as surplus sugarcane residue availability in India. It was estimated that annually 14 terawatt-hour electricity would be required for biochar conversion of 55 million ton surplus sugarcane residue having 14 million ton CO2 equivalent carbon footprint. whereas combustible volatile matters released during the biochar conversion of sugarcane residues has 52 terawatt hour electricity equivalence, which is about 38 terawatt hour surplus than electricity consumed in pyrolysis and material handling. Electricity equivalence of combustible volatile matters could reduce about 51 million ton CO2 equivalent carbon emissions. The excess electricity was considered to send to the national grid, which could reduce 37 million ton CO2 equivalent carbon emission from the national grid. It was estimated that biochar transportation and spreading would consume 27 million liters diesel, producing 73,000 ton CO2 equivalent carbon emission. In the present study, biochar produced from sugarcane residues were considered to apply in sugarcane fields. It was estimated that biochar application in the sugarcane field could annually sequestrate 19 million tons CO2 equivalent carbon in soil, 52 million tons CO2 equivalent carbon due to enhanced sugarcane yield, and 47 million tons CO2 equivalent carbon due to reduced soil organic carbon mineralization. Biochar application in sugarcane field could reduce 77,000 ton annual NPK fertilizer usage, which could reduce 280,000 tons CO2 equivalent carbon emission due to reduced fertilizer usage. The estimates also showed that biochar application could also reduce 220,000 ton nitrous oxide emissions from sugarcane fields, having 65 million ton CO2 equivalent GHG emission reduction potential. Overall, biochar conversion of about 55 million ton surplus sugarcane residues and its application in the field could reduce about 220 million ton CO2 equivalent carbon footprint, which is about 9.5% of total annual GHG emission from India at 2019 level. The carbon footprint of various factors of sugarcane residues biochar system for carbon sequestration in the soil has been shown in the figure 6. I thank you all for your attention and I look forward for your questions. Thank you.